This is Lecture 1 from Module 10 in the book Problem Solving Guide for Mechanics and Thermodynamics. This is about thermal energy and the transfer of thermal energy between two masses. This is the first of three modules which cover a concept involving energy and temperature. Here we're going to cover the transfer of thermal energy between two objects that have different temperatures. In the second module, we'll be exploring thermal conductivity, thermal expansion. In the last module, we're going to tackle the ideal gas law, thermal energy transfer, and the work done by a gas, as well as the internal energy of the gas. It's important to build a fundamental understanding of these concepts. And to do that, we're going to zoom in from the macroscopic concept of temperature to what's going on with the atoms. If we understand fundamentally what's going on with the atoms, then these three modules will be a lot easier to understand. So let's consider an ideal monatomic gas, like helium, confined in a box, like that. As you can see, the atoms are effectively point masses. They collide with each other in the walls of the container. There's a distribution of speeds. You can see some are moving fast, some are moving slow. This is natural. It's called the Maxwellian speed distribution. It's not shown here, but if these are helium atoms, the wall can't be that smooth. Right? The wall is made of atoms as well, atoms of a solid. And when the gas molecules hit the wall, they are either kicked by an atom in the solid, or they kick the atom in the solid and speed up the atom in the solid. So there's an exchange of thermal energy between the atoms and the wall, even if there's thermal equilibrium. If the container is the same temperature as the gas, the rate at which thermal energy is transferred from the container to the gas balances the rate at which thermal energy is transferred from the gas to the container. So there's no net heat flow. If the container is hotter, the atoms in the container are moving faster, they have more kinetic energy, they kick the atoms of the gas, and they'll speed up. If the atoms in the container have lower kinetic energy than the gas, they are at a lower temperature, the atoms of helium will kick the atoms in the container and give them more kinetic energy and heat them up. At the level of the atoms, kinetic energy and thermal energy are the same thing. There's no such thing as thermal energy at the level of the atoms. It's just the kinetic energy of the molecules, 1f_mv squared. So we don't say kinetic energy is lost to thermal energy during a collision between atoms. At this level, there's no such thing as heat. It's pretty clear. So here we're looking at the atoms. They're bouncing around, hitting the wall. Thermal energy is just the sum of their kinetic energies. That's what thermal energy is. It's called the internal energy of the gas. We'll see this in Module 12. The internal energy of the gas is the sum of the kinetic energy of all the atoms in the gas. So atom 1, atom 2, atom 3, atom 4, atom 5, all the way up to capital N, the number of atoms in the gas. If we sum up all of their kinetic energies, that's the energy of the gas. It's a monatomic gas. The only way it can have energy is by virtue of its kinetic energy. When a gas is hot, it's because the atoms have a high translational kinetic energy. It's not because they contain this substance called heat. Here is fast, hotter helium atoms. This gas is hotter than that gas. And if they're both in equilibrium, this container is hotter than that container. There's a direct proportion between the translational kinetic energy of the atoms of a gas and the temperature of the gas. We're going to derive this in Module 12. The translational kinetic energy of a gas and absolute temperature are related by the gas constant. PV is equal to nRT. What are the units of R? 8.314 joules per mole per degree. If you multiply this by the number of moles of the gas and the absolute temperature of the gas, that's the translational kinetic energy of the atoms for an ideal monatomic gas. E internal, sum of all the kinetic energies, which is 3/2 nRT. Little n is the number of moles. So now, once you understand this, you can say things like, the atoms in my coffee are moving too slow. I'm going to give them some kinetic energy in the microwave. So my coffee's too cold, I'm going to heat it up a little bit. The molecules in the air are moving very slowly today. You better wear your hat and gloves. The atoms in that pan have a very high kinetic energy. You might get burnt if you touch it. Because of this direct correlation between the kinetic energy of the atoms and its temperature, there has to be a minimum temperature, because the atoms are going to stop moving eventually. And that is, quantum mechanics notwithstanding, absolute zero, about minus 273 degrees Celsius. So with the idea that the temperature and the average translational kinetic energy of the atoms are connected intimately, we can think about how two objects at different temperatures exchange thermal energy to come to an equilibrium temperature. So these objects include solids and liquids as well as gases. Solids and liquids are a lot more complicated than an ideal monatomic gas because there are intermolecular forces. When heating an ideal monatomic gas, the only place the energy can go is translational kinetic. You got to get it moving faster. But in solids and liquids, there are all sorts of vibrational states, rotational states, intermolecular forces like hydrogen bonding that are not present in an ideal monatomic gas, so they're going to be a lot more complicated. So the amount of energy needed to change the temperature of a solid or liquid is difficult to calculate theoretically. And it varies widely for different solids. We're going to see examples soon, but first let's introduce the variable Q, which is the amount of thermal energy added to a substance by heating it, or the amount of thermal energy removed from a substance by cooling it. So let's think about what added to and removed from mean. It's certainly reasonable to assume that some entity is being transferred, something called heat. We're transferring heat. So if we understand what's going on at the level of the atoms, then you can call it whatever you want. But it's important to understand. So let's think about a monatomic ideal gas in a metal container, it's like helium, inside this container. We want to get the atoms to move faster. We want to raise their kinetic energy. We want to heat them up. The only way we can heat up that gas is to increase its average kinetic energy. That's the definition. So we have to hit the gas atoms with faster atoms. The only atoms that the gas atoms are hitting are those that make up the container. So we have to get the atoms in the container to increase their kinetic energy, and the way to do that, we hit them with even faster atoms. One way to get fast atoms is a flame. So let's put a Bunsen burner under there. So the atoms in the flame have a high kinetic energy. They bang against the atoms in the container, increase their kinetic energy, and then the gas hits the container and it gets its kinetic energy increased. So the hot atoms in the flame hit the container, increasing their kinetic energy, and the gas atoms hit the wall of the container. They get kicked by the fast-moving atoms of the container, and their kinetic energy is increased. So you can say macroscopically that heat from the flame flowed into the gas, but it's really a transfer of kinetic energy. That's what happened. A similar effect happens when you cool a gas. So we have this container of helium, and let's put it in a dry ice bath. So now we're going to slow down the atoms in the wall of the container. There's our dry ice bath. Now the H and the O in the dry ice bath are going to be moving very slowly. They're going to slow down the atoms of the container and slow down the atoms of the gas when the gas hits the wall of the container. You have a fast-moving gas atom hitting a slow-moving atom in the wall of the container. That gas atom is going to slow down. So we say thermal energy gets transferred through the walls of the container, and that's Q. The SI unit of Q is joules. It's energy. The problems we can solve with this understanding involve putting two materials together in thermal contact at different temperatures, allow them to come to equilibrium. So we have one hot on the right, one cold on the left. We slide them together so they can Their atoms can exchange thermal energy. And then the atoms in the cold thing are going to go faster, heat up. The atoms in the hot thing are going to go slower, cool down, and then you're going to come to some equilibrium temperature. If the two materials are the same, the calculation is relatively straightforward. So if I have 1 kilogram of water at 20 degrees Celsius and 1 kilogram of water at 50 degrees Celsius, and I put them together, the equilibrium temperature is going to be in the middle, 35 degrees Celsius. Similarly, if 1 kilogram water at 20 is added to 2 kilograms of water at 50, the equilibrium temperature will be 40. Makes sense. The problems we're going to do are more complicated because the mass of different materials can respond differently. The same mass can respond differently to the same addition of thermal energy. If you heat up with a Bunsen burner silver and water, the final temperature will be very different for the same amount of thermal energy transfer. So if I put 10,000 joules of thermal energy, Q, into 1 kilogram of water at 20, it's going to end up at 22.4. It's going to increase temperature by 2.4 degrees. If I take the same 10,000 joules and put it into a kilogram of silver at 20 degrees, it's going to go up to 63 degrees Celsius. It's going to increase by 43 degrees Celsius. So the same amount of thermal energy has very different effects on different materials. Water has a lot of thermal inertia. It's hard to change the temperature of water, as you know if you ever boiled spaghetti. The amount of energy, boiled water for spaghetti. The amount of energy Q it takes to change the temperature of a substance is called its heat capacity. Not a very good name, but we're stuck with it. Lowercase c. So the heat capacity is of a few substances, and you should think about these units, what these units mean. 444 joules per kilogram per Kelvin. Copper is 386 joules per kilogram per Kelvin. Water, 4,184 joules per kilogram per Kelvin. Ice, 2,090 joules per kilogram per Kelvin. Silver, gold, aluminum. So let's think about the equation that relates the amount of thermal energy added to the material, the mass of the material, the heat capacity of the material, and the temperature change as a result. So in the table, the last item, aluminum, takes 900 joules per kilogram per Kelvin. So it takes 900 joules to change 1 kilogram of aluminum by 1 Kelvin. By the way, since we're only dealing with changes in temperature, not absolute temperature, when we do these problems, Kelvin is the same as degrees Celsius because a change of 20 degrees Celsius is the same as a change of 20 kelvins. So how much thermal energy must we transfer to 2 kilograms of aluminum to increase its temperature by 3 degrees Celsius? Well, it cost 900 per kilogram per degree. We have 2 kilograms and we want to go up 3 degrees. To go up 3 degrees Celsius, it's going to cost 5,400 joules. 1,800 joules because we have 2 kilograms, and then we're going up 3 degrees Celsius. Makes sense. The equation is mc delta T. The C really should be first, but it sounds better if you say mc delta T. So when a hot object, high kinetic energy, think, is placed into thermal contact with a cold object, the atoms in the cold object gain kinetic energy. The cold object gets hotter, and the atoms in the hot object lose kinetic energy. It cools off. So this is really conservation of energy. This is another application of the conservation of energy. If we insulate two objects from the outside world, the amount of thermal energy lost by the hot object is equal to the amount of thermal energy gained by the cold object. So here's an example problem. 500-gram ingot of gold at a temperature of 800 Celsius is quenched in a bucket of water at 23 degrees Celsius and sealed. We put the lid on. It's a styrofoam bucket, so no energy escapes the system. So there's our gold. 500 grams starts out off at 800 degrees Celsius. Here's our water in an insulated bucket. Starts off at 23 degrees Celsius. We throw the gold in there. The final temperature is 26.5. How much water was in the bucket? So gold has a specific heat of 129 joules per kilogram per degree Celsius, or degree Kelvin. The gold and the water come to the equilibrium temperature at 26.5. So how much water is in the bucket? That's the question. We know the temperature change of the gold. We know the specific heat of gold. We know the initial temperature of the water. We can get the mass of the water. How much thermal energy did the gold lose? Went from 800 degrees Celsius to 26.5 degrees Celsius. It takes 129 joules of energy to change 1 kilogram, 1 degree Celsius. We have half a kilogram, 500 grams. So heat capacity of gold, 129 joules per kilogram per degree Celsius. We have a half a kilogram. The temperature changed by 773.5. The equation is this. It should make sense. You shouldn't have to remember that equation. So it's a half a kilogram. There's the specific heat. There's the temperature change. Q minus 49,890 joules. Where did this thermal energy go? It went into the water. The gold lost this thermal energy. The water gained that thermal energy. We have the same equation for water. Q is mc delta T. We have to focus on the water here. Q is plus 49,890. We have the specific heat of water. The water went from 23 to 26.5, so its change in temperature is 3.5 degrees Celsius. And we can solve for the mass of the water. And we get 3.41 kilograms. That's a typical problem in this module. You have to be a bit careful with the plus and minus signs when the final temperature is the unknown, because you can't set the Q's equal, because one Q is positive and one is negative. So you can set one equal to the negative of the other, or you can set their absolute values the same, either way. But it should make sense. So for an example of this, there's a video on problem 2 of practice exam 2 of module 10, in which the final temperature is the variable, or there's a problem on page 293 of the textbook that's worked through. So that's it for specific heat. I'm going to close this module, this lecture, with some phenomena of interest that involve the high heat capacity of water. One is the ability to walk on hot coals without burning your feet. If you're careful and you know what you're doing, this is not recommended. The water on your feet will cool down the hot coal significantly because water has a very high specific heat. The thermal conductivity of the coal is not good, which means that the spot where your foot touches the coal will not heat up quickly. However, a lot of things can go wrong. This happened recently in Texas. This self-help guru was asking a bunch of people to walk across hot coals to unleash the power within. Motivational speaker Tony Robbins, and a lot of people went to the hospital. You can pause and read it. Similarly, if your mouth and lips are moist, it's possible to eat flaming food without getting burned. A common demonstration is to eat a cracker dipped in rum and lit. It's no problem to do that. People eat flaming drinks if they're careful. The high specific heat of water will prevent your mouth from getting hot. That's how it works. You can go online and take a class. Fire eating made easy. Don't try this at home unless supervised. So here's also finally an energy saving tip. If you boil water for pasta in the winter and you're in Cleveland, don't put the hot water down the drain right away. Put the plug in the sink and let the high kinetic energy, there's a lot of thermal energy in that water. Let it transfer the kinetic energy to the air and then let it go down the drain once it's room temperature. If you steam vegetables in your air-conditioned home in the summer, get that hot water out of the system as soon as possible. Put it down the drain so it doesn't heat up the air, which you're trying to cool down with your air conditioner. Finally, the meteorologist often says colder near the lake, especially if you're talking about Lake Michigan, which is deep, a lot deeper than Lake Erie. Lake Michigan has a lot of thermal inertia. In the spring in South Haven, Michigan, which is on the east coast of Lake Michigan, it can be 25 degrees colder on the beach than 1 mile inland. So this happens March through August, and temperatures can be much colder near the lake than inland because the water takes a lot of energy to heat up. It's frozen in the winter, and to heat up all that water takes a long time. So it remains cold well into the summer. And then once it gets warm, it remains warm well into the fall. Also, citrus farmers in Florida protect their crop from frost damage by spraying them with water. Instead of the air cooling down the crop directly, it has to cool down the water first. And it takes a lot of thermal energy to change the temperature of water, which delays the effect the cold air has on the crop, hopefully by morning. When the morning sun comes up, the crop has not been damaged. So the second lecture for this module involves thermal energy transfer associated with phase changes, boiling, going from liquid to vapor, and freezing, going from solid to liquid.